Hey James, I just want to make this quick video for you. I put this together in terms of a Mathematica sheet so I can make decent plots for you. So I'm saying this is sine and cosine, but I'm just taking a look at the sine function for you right now, but the cosine function will have the same behavior. So here's your standard function. You know, it's the sine of x, but then you can do a times the sine of b times x plus c. So what we're going to see here is that the constant a will control the magnitude of the sine wave. B controls the frequency or the period, the number of peaks you're going to have, and C controls what's referred to as the phase shift. It's basically which way this is shifted back or forth. All right, so here is your standard plot, the plot of sine of x. So what we were saying before, that the sine of 0 is 0, and at the sine of pi over 2. So these lines here, this is negative pi, this is pi over 2, this is 0, this is pi over 2, and this is pi. So the sine of 0 is 0, the sine of pi over 2 is 1, and then the sine of pi, again, is 0. And here's the sine of pi over 4 and pi over 4. So they're equal to each other, right, because it's going up and going down. So if we take a look at the next one, so this is what happens if you have the factor out front. So that factor I'm calling a. So here's the original function, sine of x, and here's the sine of 2 times x. So in this one here, the magnitude is 1, right? It's implied that there's a 1 times sine of x over here. And for this one, the only thing that changes is the absolute magnitude. So this function now goes from positive 2 to negative 2. All right, so now what I'm looking at, now we're back to the original function sine of x, but now we're saying, all right, we won't make this 2. We'll say, hey, let's make the factor that's multiplying x 2. And this is what we talk about in terms of the period. So the red one here, which is sine of x, executes one single period when going from negative pi to positive pi. Okay? Now, if we multiply the x or the argument, right? So this would be sine of theta or 2x, sine of 2x, sine of 2 theta, whichever way you want to look at it. But if we multiply it by 2, well, then the period, we get one period here and a second period here. If this was 3, we'd have 3 of these loops, right? So I'll call it, this is one full cycle is what we refer to it. So we go from 0 to positive 1, back to 0, to negative 1, back to 0. And if we take a look at what happens if we add in this constant c, this is referred to as a phase shift. So it's interesting just to keep in mind that when you do a negative pi over 2, the function shifts this way, right, from left to right. So see the peak here? It shifts over to here. So if this was plus pi over 2, this peak would now be shifted to here. So that's one of the things that is sort of a got you in a situation, because you'd expect the positive to go from left to right, but it's the negative that moves you from left to right. All right, so if we go back to the original question, here was f of x equals sine of x. So now let's go through it. So f of x equals 2 times the sine. So instead of being 1, we're at 2. All right, so now 3x, so the period is now 3. So again, remembering that this is a single period, right? Let's take a look, right? So the single period has one upside down and one right side up. So all you have to do is count the numbers of right side ups and right side downs, right? So here's 1, 2, 3. And here we have 1, 2, 3. So now you know that the period is 3. And here we are now minus pi. So what's happened here is that this is being shifted over. So let's find out where one of the period begins. So the period begins here, right? So it's being shifted over a value. But it's kind of funky here because you're 3x minus pi, so it's not shifted over a full pi amount. And this next thing makes that a little clearer. All right, so if I just have my single pi here, and if I go and I move this over, you see what's happening. I shift from left to right. So this is the sine of, this is the function f equals a times sine of b times x minus c. So I can actually open this up. So I go from 0, and I can move over till I'm about pi over 2. Oh, it's pi over 2. It's about 0.7, right? So there, and then getting all the way around here to just around pi over 2, right? 1.57, and then I keep going. And then eventually when I get to pi again, right, so the 3.14 is pi, and I've done a complete shift. Right, so I go all the way back, so a full shift to the period. But what you see here is that I've shifted the shape of the curve as well. I would have to go all the way to 2 pi for this to repeat completely. All right, then if we go to a, nothing strange here. We're just doing the magnitude. And then here is the period. So let's see what happens here if I shift this all the way over to pi, right? Actually, let me go here, right? So it's shifted halfway. It shifted to pi over 2. Let me move it over here. See how it comes here? So now if I change the period all the way up to 3, you get this shifting. So instead of it being, see where the intersection is here, and watch that intersection, watch this intersection as I reduce this. All right, so that intersection moves over and over and over. So it moves over to pi, pi over 2 rather, and as I go all the way over, instead of being pi over 2, this value is now going to be pi over 6, because I've shifted, or I've changed the frequency by 3. You'd have to take a look at the math for that and prove it to yourself that this value now is pi over 6, or is it going to be pi over 3? It's going to be pi over 3. Anyway, hopefully this helps, and I'll send you this app, for lack of a better term, to see if you like and see if it makes sense to you. All right, so let me just stop this recording.